Assalamu alaikum. We start lecture number 29 of CS317 Operating Systems. The topic of this lecture is networking and distributed processing. We are using chapter 16 of the William Stallings book on operating system. In the last lecture, we explored the client server architecture. We explored classes of client server systems. We understood fat and thin client models. We discussed the three-tier client-server architecture. We talked about the file cache consistency problem. We discussed middleware. We were introduced to service-oriented architecture, and we discussed characteristics of service-oriented architecture for effective use of services. We continue this lecture with the subtopic Service-Oriented Architecture. Let us look at an example service-oriented architecture. This is our first example. If you look closely at the diagram, you will see that there are three databases that make up this system. One is for account information, the other is for customer information, and then there is another for loan information. If you look at the applications here, there are three different applications. Checking account web application, checking account application, loan management application. There is an external service, the credit risk analysis, which works using the loan management application. There are three clients here, the internet customer, the bank teller, and the loan officer. Different applications use different databases. Now, for each application, a single self-contained application module is built. A database management system that supports several databases ties together the various applications. Multiple applications may have access to a single database. For example, in this configuration, all three applications require access to a customer information database. Pros and cons of this example. The advantages of this arrangement are clear. By separating the data from the applications and providing a uniform database interface, multiple applications can be developed and revised independently. The approach of many applications using a common set of databases has some drawbacks. The addition of a new feature or user service, such as ATM, requires building a new independent application, although the necessary logic has already been implemented in related applications. Let us now look at another example of a service-oriented architecture. Here again we have three databases: account information, customer information, and loan information. Then we have two basic applications: checking account application, loan management application. And there are services which are using these applications. Like there is a checking account service, there is a customer vault service, there is a loan management service, there is a loan request service. And then there are applications that are working on top of these services, like the teller application for the bank teller, ATM application for the ATM customer, customer web application for the internet customer, and loan manager application for the loan officer. There are some core applications that deal with the functionality of individual databases. These core applications are highlighted here. These applications are accessible by application programming interfaces to service modules that implement common services, and these service modules are now highlighted in the diagram. Finally, The specific applications visible to users deal primarily with presentation and business logic. This architecture can achieve greater efficiency and flexibility because now if you change the underlying databases, you might have to reflect those changes to the basic applications, but you will not have to do anything to the user applications or the applications at the very top. Now we come to another subtopic in this chapter, and this is called distributed message passing. The environment and its limitations. In a distributed processing system, computers do not share main memory. Each is an isolated computer system. Interprocessor communication techniques that rely on shared memory, such as semaphores, cannot be used. Previously, what we were doing was that one processor wrote in the shared memory and the other processor read from the shared memory. And in this way, we were using variables in the shared memory to pass data. But now there is no shared memory. So we cannot use variables or structures that are something like variables. For example, semaphores, which are actually protected variables. Instead, techniques that rely on message passing are used. Message passing for client-server functionality. A client process requires some service. For example, it wants to read a file or it wants to print and sends a message containing a service request to a server process. The server process honors the request and sends a message containing a reply. Only two functions are needed: send and receive. The send function specifies a destination and includes the message content. The receive function tells from whom a message is desired. In the case of the server, the message can be received from any client and provides a buffer where the incoming message is to be stored. Message passing primitives. Processes make use of a message passing module. Service requests can be expressed in terms of primitives, the send primitive and the receive primitive, and parameters. A primitive specifies the function to be performed. Parameters are used to pass data and control information, for example, source of the message, destination of the message, length of the message, or type of the message. A primitive may be implemented as an operating system function call, or it may itself be a message to an operating system process. Let us look at the send primitive. The send primitive is used by the process that desires to send the message. Its parameters are the identifier of the destination process and the contents of the message. The message passing module constructs a data unit that includes these two elements. This data unit is sent to the machine that hosts the destination process using some sort of communications facility such as TCP/IP. When the data unit is received in the target system, it is routed by the communications facility to the message passing module. This module examines the destination field for receiver process ID and stores the message in the buffer for that process. Now let us look at the receive primitive. The receive can take place in two ways. In one approach, the receiving process must announce its willingness to receive messages by designating a buffer area and informing the message passing module by a receive primitive. An alternative approach does not require such an announcement. Instead, when the message passing module receives a message, it signals the destination process with some sort of receive signal and then makes the received message available in a shared buffer. So you can use the first approach when you are expecting a message from someone. But the second approach can be used by anybody, whether he is expecting or not expecting a message. If a message comes in, the second approach ensures that the message goes to the destination. Let us see what is meant by reliable message passing. A reliable message passing facility is one that guarantees delivery if possible. Such a facility makes use of a reliable transport protocol and performs error checking, acknowledgement, retransmission, and reordering of disordered messages. Because delivery is guaranteed, it is not necessary to let the sending process know that the message was delivered. However, it might be useful to provide an acknowledgement back to the sending process so that it knows that delivery has already taken place. In either case, if the facility fails to deliver due to persistent network failure, crash of destination system, the sending process is notified of the failure. So what is unreliable message passing? The message passing facility may simply send the message out into the communications network but will report neither success nor failure. This greatly reduces the complexity, processing, and communications overhead of the message passing facility. For those applications that require delivery confirmation, the sending application must request a delivery report and the receiving application must send another message as acknowledgement. Task 1. Name at least 2 transport protocols and then come back to the video. Non-blocking send. A process is not blocked after issuing the non-blocking send. It continues execution and goes on to its next line of code. When a process issues a send primitive, the operating system ensures that the message has been queued for transmission or copied to a safe place for subsequent transmission. If no copy is made, there is no guarantee that any changes made to the message by the sender after issuing send but before or during transmission will appear in the received message. When the message has been transmitted or copied for transmission, the sender is interrupted to be informed that the message buffer may be reused. Non-blocking receive. After a non-blocking receive is issued by a process, it continues to run and moves to the next line of code. When a message arrives, one of two strategies can be followed. The destination process is informed by an interrupt, or the receiver can poll for a status of the message buffer periodically. Analysis of non-blocking primitives. With non-blocking or asynchronous primitives, a process is not blocked after issuing a send or receive. Non-blocking primitives provide for efficient, flexible use of the message passing facility by processes. The disadvantage of this approach is that it is difficult to test and debug programs that use these primitives because the results depend upon the relative timing of the execution of primitives. Blocking primitives. A blocking send does not return control to the sending process until the message has been transmitted. This is an unreliable service, or until the message has been sent and an acknowledgement is received. This is a reliable service. A blocking receive does not return control to the calling process until a message has been placed in the allocated buffer. Now we turn towards another important subtopic, remote procedure calls or RPCs. A variation on the basic message passing model is the remote procedure call. This is now a widely accepted and common method for communication in a distributed system. The essence of the technique is to allow programs on different machines to interact using simple procedure call or return semantics, just as if the two programs were on the same machine. The procedure call is used to access remote services. Why RPCs are popular? The procedure call is a widely accepted, used, and understood abstraction. The use of remote procedure calls enables remote interfaces to be specified as a set of named operations with designated types. Thus, the interface can be clearly documented and distributed programs can be statically checked for type errors. Because a standardized and precisely defined interface is specified, the communication code for an application can be generated automatically. Because a standardized and precisely defined interface is specified, developers can write client and server modules that can be moved among computers and operating systems with little modification and recoding. And these are all the things which make remote procedure calls popular. We now talk about the RPC mechanism. The remote procedure call mechanism can be viewed as a refinement of reliable blocking message passing. The calling program makes a normal procedure call with parameters on its machine. For example, call PXY, where P is the procedure name, X represents the passed arguments, and Y represents the returned values. It may or may not be transparent to the user that he is invoking a remote procedure on another machine. Client part of the RPC mechanism. A dummy or stub procedure P is included in the caller's address space or dynamically linked to it at call time. This procedure creates a message that identifies the procedure being called and includes the parameters. It then sends this message to a remote system and waits for a reply. When a reply is received, the stub procedure returns to the calling program, providing the returned values. Now look at the server part of the RPC mechanism. At the remote machine, another stub program is associated with the called procedure. When a message comes in, it is examined and a local call PXY is generated. The remote procedure is now called locally, so its normal assumptions about where to find the parameters, the state of the stack, and so on are identical to the case of a purely local procedure call. The return values are passed from the remote server to the client machine's stub procedure. And if you are asking what is meant by a stub is a procedure that is there but does not have any functionality inside it. So it is only there to take something in and redirect it to somebody else. Another issue is how to represent parameters and results in messages. If the called and calling programs are in identical programming languages on the same type of machines with the same operating system, then the representation requirement may present no problems. If there are differences in these areas, then there will probably be differences in the ways in which numbers and even text are represented. If a full-blown communications architecture is used, like the OSI reference model, then this issue is handled by the presentation layer. However, the overhead of such an architecture has led to the design of remote procedure call facilities that bypass most of the communications architecture and provide their own basic communications facility. In that case, the conversion responsibility falls on the remote procedure call facility. The best approach to this problem is to provide a standardized format for common objects such as integers, floating point numbers, characters, and character strings. Then the native parameters on any machine can be converted to and from the standardized representation. Parameter passing. Most programming languages allow parameters to be passed as values, which we refer to as call by value, or as pointers to a location that contains the value, which we refer to as call by reference. If I am passing a variable x by value, I will simply give you the value of x. If I am passing the variable x by reference, I will give you the address of the memory location that holds the value of x. Call by value is simple for a remote procedure call. The parameters are simply copied into the message and sent to the remote system. It is more difficult to implement call by reference. If the remote machine furnishes the address of the parameter in the message, it will be of no use to the calling process because it is not an address of the machine the calling process is in. For call by reference, a unique system-wide pointer is needed for each object. This means every variable, file, or object in every computer in a distributed system must have an address that uniquely identifies its host machine and then its location within that machine. The overhead for this capability may not be worth the effort. Client server binding. Binding specifies how the relationship between a remote procedure and the calling program will be established. A binding is formed when two applications have made a logical connection and are prepared to exchange commands and data. There are two kinds of binding: non-persistent binding and persistent binding. Non-persistent binding. Non-persistent binding means that a logical connection is established between the two processes at the time of the remote procedure call, and that as soon as the values are returned, the connection is dismantled. Because a connection requires the maintenance of state information on both ends, it consumes resources like memory. The non-persistent style is used to conserve those resources. On the other hand, The overhead involved in establishing connections makes non-persistent binding inappropriate for remote procedure calls that are made frequently by the same caller. Persistent binding. With persistent binding, a connection that is set up for a remote procedure call remains intact even after the procedure has returned. The connection can then be used for future remote procedure calls. If a specified period passes with no activity on the connection, then the connection is terminated. For applications that make many repeated calls to remote procedures, persistent binding maintains the logical connection and allows a sequence of calls and returns to use the same connection, saving time in connection setup. Synchronous versus asynchronous remote procedure calls. The concepts of synchronous and asynchronous remote procedure calls are analogous to the concepts of blocking and non-blocking messages. The traditional remote procedure call is synchronous, which requires that the calling process wait until the called process returns a value. The synchronous remote procedure call behaves much like a subroutine call. The synchronous remote procedure call is easy to understand and program because its behavior is predictable. It fails to exploit fully the parallelism inherent in distributed applications. It limits the interactions distributed applications can have, resulting in lower performance. Various asynchronous RPC facilities have been implemented to achieve a greater degree of parallelism. Asynchronous RPCs do not block the caller. The replies can be received as and when they are needed, thus allowing client execution to proceed locally in parallel with the server invocation. More about asynchronous remote procedure calls. A typical use of the asynchronous RPC is to enable a client to invoke a server repeatedly so that the client has several requests in the pipeline at one time, each with its own set of data. What is happening is that a client sends a remote procedure call to a server. And since the remote procedure call is asynchronous, the client does not block. So it sends another RPC to the same server and then another RPC to the same server. It is like the client is pumping procedure calls to the server. Synchronization of client and server can be achieved in one of two ways. One way is a higher layer application in the client and server can initiate the exchange and then check at the end that all requested actions have been performed. The second solution is this. A client can issue a string of asynchronous remote procedure calls, followed by a final synchronous RPC. The server will respond to the synchronous RPC only after completing all the work requested in the preceding asynchronous remote procedure calls. In some schemes, asynchronous remote procedure calls require no reply from the server, and the server cannot send a reply message. Think of a function which does not have a return value. You call the function does something, but it does not return anything. The main purpose of the RPC is to invoke some procedure at the server and no values need to be returned to the client. Other schemes either require or allow a reply, but the caller does not wait for the reply if the RPC is asynchronous. Object-oriented middleware. Here you see that we have a client and a server, and there is a middle tier shown here which is object oriented. Let's talk about this. As object oriented technology becomes more prevalent in operating system design, client server designers have begun to embrace this approach. In this approach, clients and servers pass messages back and forth between objects. Object communications may rely on underlying message passing or remote procedure call structure, or be developed directly on top of object-oriented capabilities in the operating system. Object-oriented communication. A client that needs a service sends a request to an object request broker, which acts as a directory of all the remote services available on the network. The broker calls the appropriate object and passes along any relevant data. Then the remote object services the request and replies to the broker, which returns the response to the client. We just talked of the object request broker. It brings another broker to my mind. We have used the term broker before. What type of broker was that? Was it like the object request broker we just saw? How or how not? Take your time to answer these questions and then come back to the video. Object-oriented communication models. The success of the object-oriented approach depends on standardization of the object communication mechanism. There are several competing designs in this area. Microsoft's Component Object Model (COM) is the basis for object linking and embedding (OLE). Component Object Model is a binary interface standard for software components introduced by Microsoft in 1993. It is used to enable inter-process communication object creation in a large range of programming languages. OLE is a compound document standard developed by Microsoft Corporation. It enables you to create objects with one application and then link or embed them in a second application. A competing approach developed by the Object Management Group is the Common Object Request Broker Architecture or CORBA, which has wide industry support. IBM, Apple, Sun, and many other vendors support the CORBA approach. So, what are the lessons that we learned in this lecture? We discussed examples of service-oriented architecture and analyzed them. We were introduced to distributed message passing. We understood the different variations of message passing primitives. We discussed the RPC mechanism on both client and server side. We talked about parameter representation and passing. We discussed different types of client-server bindings. We explored synchronous and asynchronous remote procedure calls. And we were introduced to object-oriented middleware. So what are the things that you need to do at the end of this lecture? Let us revise this. You need to read the book. You need to find the answers to the tasks that I have set you. I will ask you to submit the Word file saved as your roll number lecture 29. in Google Classroom, and you will have to do that. You need to note, that is, write your questions on a piece of paper and keep that paper in front of you during the online session. And if you have any suggestions relevant to the content or quality of this lecture, you need to email them to me. This is the last topic of this curriculum, and it is much easier than the things that we have seen in operating systems. I hope that this sounds interesting to you. Take care. Allah Hafiz.